Okie doke. I'm back. We're in for another beautiful day of Fpga CPU design. Last time we worked on all this, which was implementing a simulator for the architecture just to verify that it works and figure out the timings and just try to get a golden version that can work against when I start implementing system Verilog. And we started running into design constraints of writing it in C++, like there isn't cycles, there isn't all these things that we have to add all this infrastructure for. So we're gonna work on that for a bit longer. There still is some to-do items that we have to do, right? We gotta do all this stuff. But I'll get to that later. For now, we're going to look back through the code. So we made all these files. So we go into main. Right now we just have a very simple test where we load in these instructions and then they filled out the ROB for this, right? The ROB is the order buffer, which is what handles and allows the out of order execution by having instructions entered into the ROB, because they store a bunch of information that we need. Yeah, anyways, so we got that running, and then we started working on the actual issuing and execution of instructions. So let's take a look at the code. Remember, so we were in issue, finish the ingest for reservation stations from the rename stage. So we need to fill up our issue queue, which I just call reservation station, because right now we're only going to have one functional unit, which is just arithmetic and only handles add for the moment. And we have the listening and dispatch set up. So we need to have dispatch occur for for the listening. Yeah, okay. Right, so we need to then take in these from the rename stage, right? And we need to do this so that on this will allocate a space inside of the reservation station for the instruction. So I think one of our primary to-do items, right, is implementing the stalls. As we see is number, oh, listen to that guy drove out there. We need to implement these stalls, right? So to do that, we need to have inter-process communication, or like a communication, not inter-process, so the wrong term, but we need to have communication between the different stages. Like we need to be able to tell rename that reservation station is full, right? And rename needs to tell decode that it can't do renaming because the ROB is full, or the physical register table is full, right? We need to have a can't ingest, and that needs to propagate all the way up. So we're going to start from the bottom, which is going to be from this stage, right? So we're going to create a new value. I've just been using globals, and I don't think it's like a beautiful way of doing it, but it's going to work out fine. Because also it's kind of closer to how system parallel is going to work, but it's not necessarily the point. Yeah, okay. So we're just going to put this as global signals and stuff. Okay. So a reservation station, we need to have an output signal. We should do this on paper. Okay. So on to number 8. 2026/2/6. Okay. So we need to say basically that let's just draw the hierarchy. So we have our reservation station, right? And this gets tied to the rename stage. Right, and rename also is going to have the ROB and the physical register table or file, and then rename is going to come from decode, which comes from fetch. Right, so what do we need to know? We need to know if the ROB has space, and where, right? We need to know if the PRT has space, and where. We need to know if the reservation station has space. Let's also throw the and where, because we do need to know that, but the rename stage doesn't need to know that. The rename stage, any of these three things, let's just tag them with a star. Why not? So star will invoke stall to red. So the rename thing doesn't, it technically contains these two. So we need to know if the rename stage can do rename, right? for now, let's ignore the decode and fetch, because the fetch is going to have a buffer, right? So it's going to have like even if the decode stage gets stalled, the fetch can fill up a little bit more before feeding into the decode, right? There's also going to be branch predictor and memory, a whole bunch of other stuff that I'm not going to touch right now, but it'll all have to be in there too. So, now I have to go ahead and implement this. So, we want the reservation station to be superscalar, right? We want it to be superscalar, which means that it needs to be able to intake multiple instructions per cycle. Which means that we need to be able to identify which slots are free. And communicate that back to the rename stage, right? One way that we could do this is that it has an internal routing system where basically we have, see now I'm thinking system Verilog again. We're just working on timing constraints. This is fine right now. Why don't we get a working version so we can see code execute, and then we can work from code executing and move forward, right? So right now we don't need it to be superscalar, right? We only need to know if it has space, and if it doesn't have space, then it installs rename. If rename don't have space, then it installs rob, right? And or other way around, right? If any of these are not true, then we have to wait until execution occurs, and then that execution will clear these items implicitly, right? Because on dispatch we clear the location. So there's a race station which will clear this flag, and then inside of rob, do we update rob? We commit rob. We still need to add the entire commit step. Oh dang. Okay. That's the whole point of the rob, is that it manages our exception state via commit, committing into the architectural file. Okay, we'll get there. Which is also what should clear the PRT. So on listen, should be setting present to false, right? we're just marking it as present, yeah. So then the committing is what's going to clear the PRT value, which is going to, yeah, so let's add a commit page. So let's pull back up that nice table I made here. Right. So on commit, what's going to happen is we're going to look at the top of the rob, right? I'm tired. Okay, we're going to look to the top of the rob, and we're going to see if it's being executed, right? I might have to add another flag for that. Just like an exec flag here. If it's being executed, then we can flush it. And by flushing it, what we're going to do is we're going to write back to the rat if we're committing it, right, our destination register wait. We're going to be rewriting the arf with the value on commit. And this is what takes the out of order code and puts it back in order. I don't remember why I had a last physical register destination. I know it's Grantangling dependence. Okay, let's grab that paper, take a look. Commit stage check, right? Fine. Pause this book. See the other book. Okay. Okay, we're gonna put these over the side again. Okay. So the last time I tried doing this, it seems like what I was doing instead of having an ARF is I was using the physical register table all the way through. Which is what I was using this present flag for, which I do think isn't that bad of an idea. I like the idea of having the separate ARF. I'm going to keep the architectures the way it is. It's going to be a little bit overworked, but I think I'll clean it up later. Like, there's some stuff that doesn't need to be there. Basic idea is inside of the raw. Okay, yeah. So, so inside of our raw, when we hit instruction commit, when we hit instruction commit, we know that our value has been updated. Right, which let's just write out the table and then I can work through the example instead of trying to think through it all in my head and figure out a brilliant way to say it. This stuff is too complicated to just like say, you know. So IV op PC physical register 1, present 2, physical register 2, register destination, last physical register destination, physical register destination. Okay. And then we're going to have the PRT. Just going to have I, present, free, dest, and the value, which we're just going to ignore for the moment. And then we're also going to have the R from the rat. So let's put the R here, and the rat here. We have I. The rat has ID. And the R has value. Okay. So let's say a valid office add PC is 0, P1 is true, 0, 1 true, here 2, RD is X1, L PRD is 1, 1, PRD is 0, 0. LPRD is 1, 1. That'll be from the ARC, right? New PRD is from 0, so 0, present, false, free, false, destination is X1. Alright, and then inside the rat we'd have index. 1 would be 0, 0. Right? So on commit, we have two options. We can either get rid of the arf, make everything be stored to the PRT. I think this might be a little bit confusing because if we hit an exception, then we have to like track all of this state, right? So what's happened is I've like mixed two models because I tried to. I've been reading and I tried to optimize the wrong things, right? So. What we can have happen is on execute, we write the value into the arf for this register, right? And then in this way, the arf will always be what has truly been committed, right? So they're not on execute. Execute will mark as present as a true, right? Which is great, you know? And then we could just add like a 1-bit flag because that's like cost of nothing, which is just let's just call it E. Alright, let's mark that as true. Right, so it's been executed, right? So at the top of the ROB, we check for one or more instructions being finished executing. The ones that are at the top of the ROB get committed in order, which fixes the out of order thing, right? So we can have like executed here, and then somewhere down here, more instructions are being executed inside of the ROB, right? At the top of the ROB, we see this occur. We take the value from the PRT, we copy it into the ARF for that register. We update the rat to point to is that even right? Is that a good way to do it? Because the rat could have changed out underneath us since then, right? Because the rat can be somewhere else in execution, like in parsing state. But when would we update the rat, you know? When do we update the rat back to the physical registers, right? Like once all the things have been committed, the rat needs to be pointing to all those things. Unless we keep it in the PRT. Maybe if the last, okay, so what we can do, right, is rather what we do is on execution, on committing, sorry, we're going to mark the last physical register destination as being free, right? So they can be selected. Because at this point, every instruction that will have used this previous one will have been overwritten by us in the rat, right? Yes. Which means that this will not be free. We can use it, right? Our current value is still may be referenced by other things. Still may be referenced by other things. So we're going to keep it inside of the PRT, even though its value is going to be present, right? Oh, I just don't know. I cannot. I don't. When would you update the rat? I can't. Because it needs to be updated, right? If we get rid of the ARF, we never have to update the rat. But then we need to reset the rat to the physical register table on exception, right? On exception, we flush the rob, right? And we restart from the last committed instruction. The rat will be updated back to pointing to the ARF, right? The we can just flush the PRT. We're keeping 2 copies of the data, which I don't like because that's a huge waste. But there's no way, unless using like a double redirect, but that necessarily takes 2 clock cycles instead of 1, to look up this value. Right, like we can't change the instructions in flight who they're referring to. Right, so all we can do is we're going to make a copy of PRD I should work through an example and think about this more, right? So let's come up with another example. Example page. It's gotta be in here somewhere. Here it is. So what we want to do is we want to have instructions in flight be overwritten in the rat. Right, and we want to be able to get, what I want to know is, the question is, there's not questions page. On commit, do we reset rat to OG reg / arch? Right, that's the question that I want to answer. So let's come up with an example where we can see if this is or not, right? So we're going to keep this add I instruction. Okay. hash file. I don't do one setting notifications right now. Okay. So we're gonna keep that add I. X1, X0, 10. So we want to keep this X1. Right, and then we want to rewrite this X1 with things that are dependent from the PRT, and then write to X1 again, and then use things that are dependent in the PRT. So let's do an add I X2, X0, 10. Okay. And then let's do an add X3, X2, X1, add X1, X3, X2, add X4, oh wait, that won't work. Okay, this is dependent on this. This is going to overwrite this. Okay, wait, no, this example should work, right? So we're here. No, it shouldn't work. We need to have another one, yeah. So let's do an add. Yeah, X3 is X1, X1, right? So we're to draw out the dependency graph from this X3, right? It's going to be dependent on an X1. This X1 is going to be X12. X12 is going to be dependent on X3 and on X2. X2 is dependent on nothing. X3 is dependent on X2 and X11. And X11 is not dependent on anything. So when we commit this one, when this gets executed, say this gets executed before this gets read. This gets committed before this gets read. This is still in memory, right? So these have all been parsed together as a bundle of 4 instructions, right? Let's say it's 4 wide. Then this one executes, which will reset the rat pointing at X1, right? Then we start processing this. It's going to be looking at X1. Then this will start executing after this finishes this can execute at any time based on its dependence, which is from the arf, which is always present. So this can execute any time after this instruction is present. So these would all be added to the reservation. So I can't add it back to the rat. The rat just has to get reset to the arf on exception, and I need to keep 2 copies. So let's work through the bad example, just to like do it, you know. So we need, this is valid, this is valid, let's have another 4 which is valid, and then we just have an add, and an add, 8C10. Okay, so P1, present 1. For these are going to be x0, x0. For right now, this is going to be false. This is going to be false. And this is going to be false, right? Present register 1. For 3 is going to be, need to add that, right? So 2 for x2. That's no longer free. The destination is x3. The rat, we're going to have 3 as being 2, right? And then we're going to have another one, which is 3. Not free, the destination is x1. And then 1 gets set to 3, 0. Okay. So we'll run back to x3, which is dependent on x2 and x1. So P1 is x2, which is 1 null. False, and that was 0, 0. Destination register is x3. Previous was 3, 1. New is 2 null. Then we're adding x3, which is 2 null, to x2, which is 1 null. The destination is x1. The last destination was 0, 0. The new destination is 3, 0. Okay. So now let's say that this executes, this instruction executes and gets committed, right? So 0 gets committed, and we're on to 4, right? So 0, let's do the 0 commit, right? So we're gonna say that this is now free. No, we're gonna say that this is not free. It's not free yet, right? The destination is still x1. The arf value for 1 is going to be set to 10. This rat ID for 1 is going to get set to 1, 1 in this false example, right? Then we're going to execute x1 is a dependent for, okay, wait, watch 7. 0, 0 is now marked as present. So anything at 0, 0 is now marked as present. So this is true. Okay, and let's say that number 2 or 1 hasn't finished executing, so we don't have the other ones as being present, right? We read this in. P1 is present, right? Because we're getting it from the arf. its value is 1, 1. P2 is also present. Its value is 1, 1. Its destination is x3. We need to allocate a new one. 4 false, x3. Right, previous was 2 null. This name is 4 null. That wasn't right. It was 2 null. No, I did. I'm fine. I did it fine. Okay, which then means when this gets added to the reservation station, it will be ready before this add will be ready. Right, which means that it would be executed next. Like, let's say it's a multiplier. It's something that takes a long time to load, right? This would be ready next. Which means that it would be present and its value would be 20, but its actual value should be something else. Which means 20. Should be 60, right? So we're getting should yield 60 producing 20. Implies that rat only update on exception or addition. Okay. No. Yes. Date otherwise. Bang. Okay. Cool. So now we know that, which means that we can go into our code. Right, and we can start writing this. So, well, we don't have to start writing this right now, but PRT is marked as free. Marked when rob instruction is committed. Rob last preg d is marked as free. Okay. Okay. So we need to get this thing executed in code. So this is the PRT. We don't need to care about the PRT. We need to care about we need to care about execute. Right, so inside of execute we have arithmetic, inside of that we have issue. Right, so the issue needs to ingest from the reservation station. So if we go into main, right now we are just calling these rename instructions. Right? So what we need to do is we need to tell rename I have to skip this, don't I? Yeah, that's page 8. Right. We need to tell rename that we have space. Let's just not make it super scatter. Let's say we have space and then it just puts it into the next slot. Right, so we're going to make a signal called has space. Set the issue queue. Okay, so call just a bool rs has space is equal to false. Right. So if the rs has space, this will be set to true. Right? It doesn't matter, it's a global. Okay. Rs has space is a global. So if not rs has space g, then we're going to just return. Okay. Inside of rename, rs ingest is going to take from common micro. How does this work? We need to know if they're present or not. Out of the thingy. When we're passing them along. We'll know if they're valid based on whether or not they're an immediate value or if they're ready. Oh shoot. What's good? Acophoric. Okay. How's it going? So we have these opcodes that we're sending across. We have the p-regs. We have the destination. We need to be passing. We need to be passing this has space global. We're going to be passing in a micro op type into rs ingest. That's what we're going to do. Micro op type. Micro. call mop. Oh, because that's the data that's being passed along, right? Now, we need to update the micro-op type to support these booleans. So it has immediate. It's already ready. Okay, I don't know. Do I ever use this? SRC2 valid. That's my only use. Okay, so we're gonna get rid of this and we're gonna call this SRC2 immediate. So instead of valid, well, I don't know if other instructions only use register 2. That doesn't make any sense. Yeah. Let's just make it be immediate. Okay. So bool src2 immediate, and then a bool src2 ready, and then bool src1 ready. Okay. So then inside of rename, when we are producing this micro-op, when we're putting it inside of the ROP entry, so mop dot src1 ready. We're looking these up in the rat. We need to look them up in the PRT. We need to look them up in the PRT. This is already going to be taking a cycle. They're going to be passed in. And we're going to be pulling out our PRT value. Is it going to take more than one cycle? When we look it up in the rat, do we keep if it's present in the rat too? I mean, it wouldn't be hard, right? And then we would just make the rat be updated that way, because then we don't need to, the arc values will set the rat to be ready by default. Yeah, let's change the design a little bit. Get us up with the rat. So the rat entry will have the ID and it'll have a boolean for present. Right? Okay. Okay, and mop dot src1 dot ready is equal to, let's just make this be rat okay, so now we have them both being ready. And then inside of the decode stage, we need to know inside of the decode stage, we need to know if it's an immediate value or not. So we should pass that in along with the instruction. Okay, so let's go back to common. So let's go back up to instruction. And we're going to have a bool, which is source to immediate. And then inside of our micro op, we'll also be using that, right? Yeah. So then op.src2 immediate is equal to inst.src2 immediate. Okay. Which means we're always going to have to update the test. Op source 1, source 2. Let's choose your test, source 1, source 2. And then if it's immediate or not. Okay. What's wrong with you? Oh, I've lost some amount of information here. Add one plus. Okay, so I should add back. Add I x2 x2 5. So add I 2 2 0 1 x 1 8 5. Add I know that's fine. Okay, whatever. Let's go back to planet. Rename. Rat. Your T is supposed to be what? Five, 1, 2, 1, 2, 3, 4, 5. Is the rat. I need to update these present tags when I'm adding back to the rat. Zombie jet girls. Okay. Update the rat to point to our new instruction. Okay. Let's recompile that. crazy that this takes this long to compile. That's wild to me personally. Alrighty. Yeah, so 0 now gets updated. What we could do is have from our instruction we don't want to overwrite the destination if it's writing to x0. Right. So yeah, so if inst dot dst is equal to 0, point 1, don't allocate. If insertion test does not equal shoot. Well, I don't know what that keybind was, but it did something. I didn't know that did that either. Okay, does it work? No, it doesn't work. Dang. That's really annoying. Step 2, determine dest. Builds. Step 2.2. BSD is equal to okay. Okay. That should be all set up now for the X zeros. Now presentness should be able to be determined out of the rat. Mm-hmm. Okay. So that is rename instruction. The rename instruction should now produce a mop that looks like what we want. Right? Oh. We now need to update the rat so that on it looks like the PRT wasn't a few. Okay. So the rat does not need to Freg in art. FU signal should never be going to art. That's true. Okay. If rat signal is already present, yeah, let's keep that. FU signal should never be rat. We're just marking if it's present. Cool. So now the rat is ready, which means we can go back into signal handler and comment, which does nothing. Okay. Okay. So now all we need is for no signal from your device. What is displays doing out here? There we go. That's what you're supposed to look like. Okay. No, it might be one. Okay, so now we need to connect from the issue queue. Alright, we have RSS space. We're ingesting a micro op. When do we determine if we have space? That's a really good question there, Self. I don't know. We'll do that in a minute. Let's get back to the rename stage. No, we'll go back to main, actually. Okay. Don't know why you're throwing me there. It's rude. So we're calling all these rename instructions. So, let's go ahead. Alright, I don't keep it close. So annoying. Alright, let's create a new function called void manager. Okay. So we're gonna have a set of instructions. For now. Okay. Good. So we're gonna have a set of instructions, and then for each instruction, what we're gonna do is step 1, decode the instruction. Step 2, rename the instructions. Step 3, dispatch the instructions. Step 4, listen for signals. Step 5, manage signals. Okay, so decoding instructions we're going to skip for the moment. We do. This. Step 2 for renaming the instructions, we have rename as a function set up and working. So we take in rename instructions. So we're not going to make a superscalar, we are going to make it out of order for the moment. So if Okay, so we're just gonna do call rename instruction micro op type mop is equal to rename instruction. We're just gonna take in inst. Right, we're just gonna make a instruction type inst. Put it in 0. Okay. And dispatch the instructions, which is going to be fu. Nope, not fu. It's going to be rs ingest mop. Rs ingest is going to add it. So let's do if rs has space g and prob has space g and here t has space g. Then we can rename. Step 2.1 check. What are they? It's continuous. Values. Step 2.1 check continuous values. First piece of thing though. That's because it's not. Okay. So let's go to Rob. We can just read not Rob full. Here space. void update purity Yay. I know that's not how you spell that word. I just don't know how to spell it. Right. Okay. Rob is going to be self-managing. Okay. Let's do ingest. Otherwise, is not reserved. Marvelous. So. Ooh, you don't need an M in here anymore. Right. Where are we going? Okay. It's gonna be common, right? Nope. Wait, what? Okay, we're just gonna have to read from the PRT. Okay, yeah, so source 1 is ready. No. Okay. So now it's been ingested. Instruction dispatch happens as when it comes as far, it only comes as far. Rob, rat, PRTRS. Okay, so let's actually make this step 4 and make this step 5. If you ready, true. Probably got rid of that. Okay, I need to go to the issue queue. So if we go into dispatch, what's dispatch happen? Dispatch occurs. Then we would run all of these. Oh, Lord, when he's stupid. FE signal trying to overwrite present value, dispatching add I. Okay. I don't think that this is the way that this is supposed to work actually. I just copied the rat out of the PRT, right? I should have not been doing that. Let's look at the rat. The rat is mapping to a P-rig, and if we go to execute, we'll see that the FU signal destination is going to a P-rig destination. So what we actually need to do is we need to make it like the reservation station. Yeah. Like this. So if rat at I dot D is equal to signal DST, we can keep that for sure. Unless I should put that first. Rat. Ooh, lordy, look at them. Those are values. They don't look particularly good, but they're in there. Cool. Just listen to those executing signals. Add. Interesting. Yeah, CVP. Add. Well, dread. Oh, why did I do that guy, girl? That was one way to do this. Here. Oh, I need to add to the Rob. So here, I added a ready for commit flag. I don't use these presents. I don't think. FEC could also should be. I don't know, I wrote it as a capital FEC. I don't think I need these presents in the Rob because I'm putting them. In the PRF. Yeah. PDST is equal to signal with DST. There you go. Okay. Yep, okay, y'all are ready for commit, which means that y'all should be executing. You two aren't. We're adding 3 0 to 0 0. 4 to 3. Okay. Add 4 0 and 3 0. Four zero. So you don't get executed. Bloody. Okay. Let's go to main. Get rid of these. I forget how you do that, Jesus. Okay, cool. So we can see that this immediate value is wrong. Still. That's a 10, that's a 10, that's a 10, that's a 10. It's not wrong. Wrong is the dead beef from UX0. You're looking up in PRT. She might not be from PRT. Okay. Send me with Venice macros for some comment. Okay. So, do this. Otherwise, where did I put my phone? No, there it is. Okay, so we have Ada. I think that's doing the computation correctly. Looks good. So I think we should actually set up scheduling somewhat properly. Let's finish commit actually first, because commit doesn't need anything else to work. So on commit, as we worked through earlier, type of struct, what's it going to be called? It's going to be called Wahab. Yeah, signal type. So what's inside of a rob? Rob has valid exception code. So the rob has to touch when it commits. It's going to update the PRT and the ERF. And it's going to update the ERF by writing to the ERF directly instead of sending out. I mean, I guess it would be sending out a signal. So the ERF just needs to know the destination register, and the PRT just needs to know the index. It just needs to be told the index. And we're just marking it as true. Okay, so rob commit PRT signal, rob commit valid. And then we just need the reg value. And then for commit to the ARF, all we need is the valid and reg ID. Yeah. Okay, so let's go over to the ARF. Let's do this. So it'll just be what do we call it? Yeah. So it'll be void ARF listen rob. Yeah. Okay. And you're going to take in a commit ARF signal type and signal. You're going to put nothing, so we're going to do if signal, if not, otherwise ARF add signal.id. Oh, I also need to pass the value. What signal value? 32 type value. Cool. And then let's go to the PRT. PRT listen rob, which takes in the rob commit PRT signal type. We're going to call it signal. And we're going to do if not signal valid, return otherwise PRT at signal.id. So then instead of the Rob, we need to send out what did I call it inside of the issue stage? Called it not dispatch, unjust, void, Rob, decomit. We only commit one is at the head, so we're gonna check if at head dot ready for commit, then I'll get a tail actually. Yeah. If the tail is ready for commit, then G dot arf D equal to E dot DST for our and value. It's not stored. Not in the Rob. It's gotta come out of the PRT, whatever. So PRT, this is bad design. I don't like this design. This is annoying me. E dot PST. And it's a preg to PRT. Ooh, annoying. Annoying. There we go. Okay, PRF valid is true. We just need the ID. Okay. Rob tail dot and we can do an advance. Let's go with pre-Rob tree. If signal G dot arf dot valid okay. Signal manager commit, Rob does a commit. We finished the R. Listen Rob. Where T listen Rob. Okay, so then we're gonna go into main CPP. Dispatch the instructions. Manage the shipments. I guess I can do it here. Right? For this though. What did I call it? Have to commit. And then we're gonna do PRT listen Rob, and it is Rob signal G PRT. Did the feeling afterwards. Oh, okay. I'm in a great mood for a week later. Okay, Earth. Find a way to get it done. Bang, bang, bang. Okay. Cool. Add. Cool. Stage changes, commit changes. What's the commit going to be called? It's going to be called finish execution model. SUQ and signals. Okay. So the next thing that we're going to work on, because all hard programming happens at the desk on paper, is we're going to figure out how we're going to do what's it called? Signal passing. That's not right. Clock cycles. Yeah. Where's the one I've been streaming for? Loading. Somebody showed up at some point. Sorry to it. Thanks, man. 2 hours 47 minutes. Nice. Okay, so drawing happens on the computation happens on the thingy. On the paper. So we need to figure out clocks. We need to make a unified manager for clocks. So how are we gonna do that? Do I even want to do this? Yes, I do. What are you talking about doing? So not everybody can have access to everybody else. It's going to be the problem in System Verilog. So how am I going to get the Rob to commit to the ARF? The Rob could trigger a commit. Or it could detect a commit. And it could tell the physical register table to commit. No. I feel like using the physical register table adds a layer of interfacing I don't need. Like, I could make the Rob and the physical register table be mixed together, right? Like, I could make the Rob I don't know, right? Like, Um, I think I'm gonna take a break, eat some food, and then I'll get back at it. I'm just reading through like the code. Oh, what am I gonna do? I need to change the architecture. This is good that I did in C++ instead of in Verilog, because that would have been damn annoying.